Hi, welcome to my channel, Math Made Easy with Laurel. I'm Laurel, and in this video, we're going to take a look at optimization problems. Optimization problems are also called maximum and minimum problems, and they are typically fairly challenging for students for a couple of reasons. Just like related rates, the problem is often expressed in words, and you have to come up with the function, and that might involve prior knowledge in geometry, trigonometry, and so on. So that comes into play. And the other reason is that you might have more than one unknown or one variable, and you will need to be able to express all of the unknowns in terms of one variable. So all of that, makes it more challenging and can cause students a lot of stress. But I am going to go through some guidelines that you can follow that hopefully will help you. And I'm going to go through some examples that will also give you an idea of the kinds of questions you're going to encounter. Optimization problems will often have words like most, least, fewest, greatest, and similar words in them. So when you see those kinds of words, you hopefully will understand that means if you want to find the most of something, you're finding the maximum. If you want to find the least of something, you're finding the minimum. And we've talked in the previous video how to find maximum and minimum points. So once you've got your function, the steps afterwards will hopefully be familiar to you. However, sometimes you won't have those words to indicate that it's a max-min problem. You might have, how high will something reach? Well, that means maximum. If it says how high will it reach, what maximum height will it reach? Just be aware of the different ways you're going to be asked to do maximum and minimum questions. So to start with, I want to talk about some guidelines. The biggest thing to do is to figure out what exactly is being optimized. And you might make a little statement just for yourself. Area is to be maximized, or volume is to be minimized, or whatever. Once you've got that function, then you want to figure out what the equation is that represents that function. So if it's volume of a rectangular solid, volume of a cylinder, area, whatever. Once you have that, then you want to try to write that function in terms of just one variable. So for example, with volume is a function of length, width, and height. So you will want to write length, width, and height just in terms of one variable, because if you've got more than one variable, you're not going to be able to differentiate it. So the first two steps are going to be the most challenging for you. Figuring out the function or the equation for the function that's going to be optimized, or that you're asking to optimize or find the maximum or minimum, and then to write that function in terms of just one variable. Once you've got that, the rest you've done before because you found maximum and minimum points, and that's really what you're doing. So once you get past there, then you're going to differentiate the function, set the derivative equal to 0, you're going to solve it, you're going to test to make sure it is a maximum or minimum point. And then one last step, you're going to check the problem and make sure you've answered what the question asks. Because sometimes the question will ask you what the maximum value of the function is, or minimum, or it might ask you what value gives you a maximum or minimum function value. So just be careful that you've answered what the problem asks. Let's get started looking at some examples. Our first example is a fairly typical example that you might see. It says an arrow is shot directly upward from the ground and its height is given by the function s equals negative 4.9 t squared plus 45t, where s is the distance in meters and t is the time in seconds. The question says, what height will the arrow reach? So what we're going to do is differentiate this. So ds dt, or s prime, will equal negative 9.8t plus 45. We're going to set the derivative equal to 0. and we're going to solve. So we get a solution of 4.59 seconds. Next thing we need to do is we need to test whether this is indeed a maximum. So if we did our first derivative test, we can pick any number that's less than 4.59. I always like a 0. We put that value into our derivative, and when we put a 0 in, we get a positive 45, which means that the function is increasing. Then let's take 10. 10's a nice easy number to work with. So negative 9.8 times 10 is negative 98 plus 45. That's going to be negative. So we know the function is decreasing in that interval. So therefore we know that this is a maximum point. Our last step is to check. Have we answered the question that the problem asks? The problem says, what height will the arrow reach? It did not ask at what time will the arrow be the highest. So we haven't finished. We've only found the time. So in order to find the height at that time, we plug that value into our function. And we get a value of 103.3 meters. So that arrow will reach a maximum height of 103.3 meters. I really like this second example because it looks like a straightforward question, but typically students do it incorrectly, and I'll explain why. The question says, what is the minimum slope of our function? And what I see students do is right away they find the minimum value of the function. That's not what the question said. It didn't say what is the minimum value of y, it said what is the minimum slope. So in this case, we have to come up with the function that represents slope. So how do we find slope? We take the derivative. Now I'm not going to use y prime as notation because then it might be a little bit confusing. I want to have a letter that represents my function that I want to minimize. So I'm going to just call it m. The function for slope will be the derivative of this, which is 6x squared minus 6x. So this is the function to be minimized, not this. So be very, very careful. I need to differentiate this function. So now I take the derivative of the slope. It's going to be 12x minus 6. I set this equal to 0 and I solve. So x will equal 1/2. Once I get a value, I need to test it. So I'm going to test the derivative with a number in this interval, which could be 0. When I put a 0 in, I get a negative. So the function is decreasing. And then to test in this interval, I can pick the number 1, put that into my derivative, and that gives me positive 6. So the function is increasing. So therefore, this is a minimum point. Now we have to check. The question said, what is the minimum slope? It doesn't ask the x value where we have a minimum slope, so we're not quite done. So the minimum slope will be the slope at x equals 1/2. So that slope will be 6 times 1/2 squared minus 6 times 1/2, negative 3/2. Let's try one more example. Our third example is going to be more challenging than the previous two examples. In the first example, we were given the function that we had to maximize. In the second example, we were given a function that we had to find the derivative to get the function that we had to minimize. But in this example, we're not given anything. And this is very typical. I think every calculus textbook has this question in it. So the question says you have a piece of cardboard. In this case, measures 40 centimeters by 25 centimeters. And you want to cut squares from each corner and then fold up the sides to make a rectangular box. It often helps to make drawings when you're doing these problems. I'm very limited in my drawing skills, so it may or may not be helpful. But when we fold up on, after we remove those corners and fold up on the dotted lines, we're going to have a rectangular box. And the thing that we want to maximize when it says find the largest box is we want to maximize the volume in this box. So that's the function that we need to start with, volume. And the volume of any rectangular solid is length times width times height. So the volume depends on 3 different variables. And in order to do optimization problems, you only want one unknown or one variable. So we're going to try to write volume in terms of just x. So I'm going to let these corners be x. And then I'm going to express this length as 40 minus x, so it will be 40 minus 2x. Similarly, the width will be 25 minus x, so the width will be 25 minus 2x. And the height, when I fold the sides up, will be x. So these are how I'm going to express length, width, and height. Now we have volume as a function of just x. I'm going to multiply all this out because I don't want to use my product rule to differentiate. So I'm just going to expand this polynomial. This is the function that I need to maximize. This is the function I differentiate. I'm just going to rewrite the derivative and change the order so that I've got my x squared term first. Now I'm going to set this equal to 0. This is a quadratic equation. I could use the quadratic formula, but in this case I can also factor. So I'm going to factor. So I'm going to factor out of 4. And then my factors are here are 3x minus 50 and x minus 5. Now I can solve this equation. I'll get a solution if 3x minus 50 is equal to 0, or if x minus 5 equals 0. I have two solutions to this equation. However, if I think about the problem, I can't take a corner of 16.7 out. It's just too large. I won't have a box left. So I'm going to discard that solution. And this is my solution. That's the value I want to test. In order to test this, I have to be aware of the 3 intervals. Even though I'm not going to consider this as a solution, I need that there because I've got the 3 intervals. So I'm going to test the first derivative in each of these intervals. So I'll choose 0. When x is 0, we have a positive times a negative times a negative. A negative times a negative is a positive. So the function is increasing. Let's pick 10 as the number in this interval to test. Positive. So 10 times 3 is 30 minus 50 is negative. 10 minus 5 is positive. A negative times a positive is negative. So the function is decreasing. So we can see that this is a maximum. And we're not going to worry about that point because we discarded it, but we just have to be aware of it as a boundary for our interval. Now, let's see if we've answered the question. The question says, what size of square should be cut out? So the size would be 5 centimeters by 5 centimeters. It doesn't ask for a maximum volume, so we don't need to find it. I would like to do more optimization problems and just progressively get into more challenging ones that you might see, but try some easier ones to start with. Try to find some that are similar to this and see how you make out. And then when you're ready, take a look at the next video. Take care and see you then.